Good afternoon. I'm Rocky Capozzi. On behalf of Alaska Public Media and the Alaskan Aviation Safety Foundation, welcome to Hangar Flying. This afternoon, our guest is retired UAA professor Michael Buckland. Michael served as a designated pilot examiner for approximately 25 years. He has about 12,000 flight hours with about 2,000 in seaplanes. He holds an airline transport pilot rating in both helicopters and airplanes. And at one time, he taught for the American Airlines Flight Academy. Welcome, Michael.
Thank you for having me, Rocky.
So for our audience, last time Michael was on, we began a discussion of practical aerodynamics. I'd like to continue that discussion today. The last topic we discussed was pitching, in the event of an engine failure, pitching for optimum glide, and when is it appropriate, or is it appropriate to change that from maximum glide to some other speed.
And what we're starting to get into is the fact that best glide speed will get you the furthest distance, which is appropriate, but it's not necessarily a safe or appropriate contact speed if you're hitting obstructions. And so if you take a typical airplane with a safe margin above stall of 50, either miles an hour or more modern aircraft, higher powered 150 knots, and it may have a gliding speed of 70. Well, 70 represents actually a 40% increase over 50, and everything is going to be increasing at the square. What that means is if you have a 10% increase in contact speed, you have a 21% more violent impact. A 20% increase in the speed at which you hit anything, you'll have a 44% increase in the violence of the contact. 30% increase will give you 69%, 40% increase would result in 96%. In our example, Rocky, we're talking about a 40% increase, 70 over 50, and that would almost exactly double the violence of impact, and in that case, the likelihood of serious injury or worse.
Okay, so what you're saying is once you get to the landing area, you feel like you got it made. Now you really want to manage your energy so as to touch down at the slowest possible speed, but not stall.
Absolutely. There's an old rule that you don't want to run out of airspeed, altitude, and ideas at roughly the same time.
Fair enough. So one of the most important equations and concepts in aviation is the lift equation. What are some significant items, if you will, in terms of practical aerodynamics that emerge from the lift equation?
The lift equation is one that a lot of pilots aren't particularly that familiar with. It's just lift is equal to the coefficient of lift times 1/2 air density times the velocity squared times the lifting surface area. But the two parts of that are extremely important in flying decisions, Rocky, are that we stay alive by producing lift, maintaining it. And there are two ways we can do that in practical terms as pilots. We can do it either through the angle of attack controlled by the elevator, or we can do it through the velocity through the air. But that velocity is squared. So if you, other things being equal, if you double your angle of attack, you only double your lift. Other things equal, if you double your velocity, you have 4 times the lift. And unfortunately, it works the other way. If you cut your velocity in half, you only have 1/4 the amount of lift. And that's why sometimes airplanes tend to come down out of the sky.
Roger that. So, you know, keeping all that in mind, what's an example related to takeoff distance and velocity?
Okay. Well, let's say that you have an airplane that can easily leave the ground at 50, either miles per hour or knots, depending on your airplane. If you could leave it at 50, but you stay on the runway until 55, that represents a 10% increase. You will automatically burn up 21% more runway. If you stayed on until 60, 20% increase, you would use up 44% more runway. Exactly the same situation will be true on landing. If you could land a touchdown speed of 50, but you choose to touch down at 60, you need 44% more runway, which you may not have.
Pretty important concept there. And how does, I see we've got about a minute left here, but how does velocity interact with drag? What's the relationship there, velocity and
Well,
drag?
both lift and drag are going to vary as the square of velocity. So for example, if you're in a seaplane and you're touching down and you're faster than you need to be, maybe you're 10% faster, the sharp hydrodynamic drag in the bottom of the float and the resulting nose-down pitching, that's going to be 21% greater. The same is true, of course, with turning. If you do a turn at 60-degree bank, twice the airspeed going in, you'll need 4 times the canyon area to complete the turn.
Good point. So, you know, we haven't really discussed things in any detail in terms of mathematics, but the idea is pretty clear. It's important to be on speed for whatever maneuver you're performing, I think is one of your messages.
And a very important mathematical reality for aviation is you don't want to scare yourself half to death twice.
Fair enough, Michael. It's been a pleasure having you today. We look forward to seeing you again.
Thank you, Rocky.